Hey guys, this is Brad Dyke. This is part of my future what if possibility videos. And it's based on what we see in the industry today, what we're faced with for tomorrow, and what most likely will evolve into the future. So, with that, today's discussion is going to be about storage. The key thing about storage, it's not what we think it is. If you know anything about storage and you've seen some of my other videos, you know I have this circuit board that's so big and so wide, and it's got 3 or 4 boards that are all screwed together, and they have this crisscrossing of copper wire and these little beads. They're called ferrite beads. And every time a copper wire and a ferrite bead crosses, you get a bit right there in that ferrite bead, and it either receives a positive or a negative charge, as I understand it, and that makes that 0 or 1. And these boards were by the thousands, and they would sit in these racks, and that would give you 40,000 K. Not much, a drop in a bucket, nothing compared to what we can do today. But this size is very important because it's going to teach us something about storage that we're not thinking about, but we actually know is to be the case. When you're dealing with storage back in the days of copper ferrite combinations like I just described, getting memory was hard. Over time we figured out, well, what if we took little pebbles, on magnetic pebbles, call them that, which is, it's a kind of a paint that's got a magnetic cohesion to it and stuff like that, but too technical for me to go into right now. But let's just say they create these little pools of magnetic attributes, and then you run a head over them, and you can read them for what they are, or you have a right head. It will change the polarity from a 0 to a 1. And we put these all around these things, and we call them platters, right? And so by doing that, by putting them on their platters, per se, we can get away from the complicated copper wires and ferrite beads, and we can make a virtual version of the ferrite bead. Very important detail. Don't forget that for later. And we called them platters, and we'd have a bunch of these platters. This is a very old 28-year-old hard drive. It was a 5. I think it was a 5 gig platter, and it had like 4 discs with it. And it went chicka 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 because the arms would go over it and read the surface area. And this material that you see that's on this silica disc footprint, it is basically kind of like a paint, kind of. I won't go into the details on that because there are so many different ways this was done. I'm sure I'll get it wrong. But my variations of them, I mean, this is a very old one, and this would hold very little data because the heads were gigantic. Everything was big, and there was nothing really well defined. And eventually, they evolved into a more surfaced area strategy for data storage. And again, this is important. There's nothing there, guys. It's just a surface and how we treat the surface. And then, see, they're even smaller. You can see the outline of the disk right here compared to the disk I have beside it, compared to the disk I have here, and compared to the disk I have up there. And it is big. Hang on a second, I'll show you what I'm talking about, how big these got. So remember, I showed you this disk and the material on it, and thinking, wow, that's a big disk. That's far greater than the size of a 3.5 inch drive. Look at how big that is compared to its brethren. But then when you go over here, look at the size of these disks. This is an inversion process system here. Let me take this off. This is, compared to its brethren, the kind of systems that I worked with many years ago, and these came from the old mainframe environments. We tore these apart and retired them, and of course I was able to get them, and if you're looking at this device, it is highly complicated. It is an inversion field generator. I've only been successful with building it once, but the key detail here is when we started with these, we had these giant heads like these, and they would tag and read off of these platters to give us the capacity and read functionality. Over time, we got it smaller and smaller and smaller, but we also changed the format where we had a magnetic comprehensive compound like you see here. These are more disks that have been added to the inversion process, and the plasma field generator that generates the magnetic effect. So the key vulnerability of these guys is they could be wiped very quickly. So any data you had on them literally were null and void. And over time, they got better with it, but it never really took off very well. So the end result was that they turned around and evolved into a surface-based tracking of data versus an applied surface, like you see here. Now, what's so important about this? Well, applied surfaces means you can actually use the surface of something more effectively than you could have if you put a membrane on top of an aluminum plate or a silica disc or something like that. And the end result would be a different way of storing information. So, now, what's bad about discs? Well, you would need a whole bunch of them, right? There's 50-40 here, right here. And that's not feasible. Again, we have a new problem. Even though these have gotten smaller and smaller, they're still huge, right? By the way, when you handle these, make sure you wash your hands because there's carcinogenic compounds sometimes on these. Just to be cautious, wash your hands. But the key thing is we're starting to pick up on this new idea. If the surface is actually the attribute, what if it's the placement of that little bit of information, that byte of information that's 8 bits? What if we could layer that? True. We did that, actually. We call it RAM, random access memory. But the problem with random access memory is random access memory loses its data integrity when it loses power. Hence, it has to be repopulated. So you have to load everything off of a hard drive back into the memory so it can operate. And that it was quite an Achilles heel for a long time until SSDs. This is not the end. SSDs reformatted the nature of memory, random access memory, and made it approachable, also referred to as 3D NAND memory, approachable from different aspects so it can be given charges that it will hold. That's the big difference between RAM and SSD disk RAM storage, or disk memory storage, probably the correct term I would suggest to use, and not the word RAM. Then they got better at it. So they started to create a smaller and smaller put. But the key thing they're missing here, and this is where the future is coming, is you don't necessarily have to have a static environment for storing data. If you can attribute the nature of a placement in a volume of space, it will still be there. If you can strike the area, create the charge, or be able to read a 0 or a 1, or if it's small enough, and this is where quantum computers can get in, they can be 1, 0, or 1, 0. 3 different states. Now, how can that be done? Well, we kind of already do it. We don't do it with a cup of coffee. Theoretically, you can if you have the right type of, well, reading and writing head, right? One of these guys. Except these would be more of an encompassing housing. And they would cross-intersect through each other. It's very similar to how lasers would strike each other from different attributes because they have, there are a lot of little micro lasers all around. And they strike the areas to create a polarizing effect. Now, we do this with magnetic effect and electricity in blocks of memory chips. Okay? So we've got the foundation. We know how to do that. But can we take it to a new format? And the area there is, what if we could take a box like this and it's completely empty except for the bottom, the top, and the 2 sides. The top, bottom, and the left and the right, not the back and the front. But at the back and the front would be valuable too, and could increase the ability of using the space inside. Then inside the environment, there's a polarized, what do you call that word? I'm thinking of inert compound inside. Anything would qualify. It just doesn't need to change. That's the only key prerequisite. Then the sides, using their transmit points and receiver points, strike the areas within that inert media and alter it. This hard drive could be the equivalency of 1,000 petabytes. This one little guy right here, because that's how much true capacity you could do on that inert material. The only difference between that and this is the chips are pretty small. But you could fairly effectively do it here as well, because once you tag the particle and you change its polarity, it's a 0 or a 1. It really is applicable. But can you go farther than that? Can you develop a technology that does what's called engram bubbling? And what that basically means is it creates a tiny little St. Elmo's-like tiny ball lightning, or what's called a closed loop parity ball of electricity. And what it is, it's got everything perfect that it needs to maintain the circle. The circle called the encasement or the bubbling effect. And we know it exists. We can make it. We make it in many different ways. It's used. This technology is used to put out fires, and we see it on airplanes when they're in altitude. It's basically a small little ball of electricity that has just the right amount of variances that meet each other's side's requirements, so the negative and positive are switching back and forth equally, and so therefore it creates kind of like a ball of lightning. But what if you could do that on a super tiny scale, like 5 electrons or something really small, but you're doing the same thing. You're injecting just enough electron energy of negative and positive charges into it to create it and give it stability so it stays there. This happens all over the world, every day, everywhere. And we can't see it, but on a rare occasion, when it's such a high amount of voltage involved, it's visible to the human eye. But we know that these effects exist and they are in there. So what if all we did was we take the same kind of strategy, and now we're not talking about a particle. We're not talking about, something big. We're talking about the things that make the particles. We're talking about electrons. And you turn 1,000 petabyte solution into an ungodly infinite value of capacity in that same platform. But do you need the case? There's the trick. There is the challenge. Can I just get rid of the entire housing? And instead, can I have devices that have the ability to create it in an environment all around us, and it be in the environment in a secured facility, and it contains all that data, the reader and the writer. And those are your prerequisites. So you'd have a couple 100,000 of these guys and a couple 100,000 of these guys, and they are charging the air and attributing the air. They're not making anything special. Everything inside that environment is neutral. There's exact amount of negatives and positives. That's the whole point about creating ball lightning, is it's self-sustaining. And if we figure out that math, then we can eliminate the need to have any kind of storage in the future. We could keep it out in the open, very similar to the way we transmit wireless power. So I'll never see this ever come to fruition in my age, but all of the basics are here. We have all the technology. It's just the time it takes to transition to that kind of mindset. The other key value to that is, unlike serial-based computer systems, those systems could not logically access those future variations of either airborne memory storage capacity or highly particulated storage capacity models and so on, because they don't have the bandwidth and the bus speeds necessary to able to view that data correctly. So quantum computers will have a lot to do with that equation as you go into the equation, because they have the ability to go in and out and in the middle. And that's the kind of busing that you need to be able to draw a single picture. So would this ever potentially come to fruition? Possibly. Where there's a will, there's a way. I mean, Star Trek had the little flip out communicators. Well, geez, that went off like a bang in the United States. So I can't see why not, because I think already we're kind of heading in that direction already, specifically with particular style storage capacities. In other words, we're making 3D RAM style memory storage capacities on steroids, and they were staggeringly thick chips, and it's the same kind of strategy, but all of the inert material that you're using in that equation, minus the points where you can polarize, those things are fixed. They're in a located position. They'll never change ever again, and that's a good thing and it's a bad thing, because eventually you run out of capacity and you have failures and stuff like that that occur that you have to plan for. So with that being the case, we're definitely going to see more progression when it comes to storage. And we will also, just like we see now with CPUs, RAM, hard drives, and many other types of technologies, we will crest on how fast we can use that capacity. Both on two principles. One, there are always limitations on data busing. In other words, how fast you can move data back and forth. Two, our brains. We just can't take in any more than a specific amount of input. Our eyes can only see 30 frames per second, and so on and so on. So our own input-output devices in our bodies are part of our limitation. So with those key details, it's neat to kind of think this way, because now you can see the next progressive logical step in the equation. And computing actually, and I think this is going to come to fruition, and it already has actually, correction, it already has started to happen, is that capacities now can be compute functions too, which means you can reorganize the nature of how you're using the memory capacity here and turn it into a CPU. So that might end up being the inevitable result, where RAM is acting, where I should say not RAM, but that your media forum will not be called a hard disk. It won't be called RAM. It won't be called CPU. I don't think GPU will apply because it has special needs. But pretty much everything else could be constructed out of the resources on your principal capacity device. We already have technology in play today that does take memory and reconvert it into a processor. We have technologies today that take disk storage and use it for crypto computing. And we have many, many, many other things. It's what you guys think of when you look at something outside of the box it's sitting in. That's the secret sauce, and that's the kind of stuff that's exciting. Well, this is Brad Dyke. I'm going to let you guys go. God bless. Take care. And I'll be away for several days. You have to deal with a funeral and stuff, but we're getting there. I'll let you go. God bless. Bye-bye.